In this video, I want to talk about projectiles. Okay, a projectile is something moving under the influence of gravity, and we've already talked about simple projectiles. If I drop a penny off a bridge, it falls straight down. Okay, and there's kinematic equations to solve that. But what about a more complicated projectile? All right, for example, suppose somebody runs off a cliff. Let's say they're jumping into a lake, okay, or diving into a lake. So that's going to make a shape that's going to look something like this, right? Or what if somebody hits a baseball or a golf ball? That's going to go up, right, and then it's going to go down. Okay, can we handle mathematically these more complicated projectile motions? All right. Now, before we explain how to do that, before we work it out mathematically, there's a big idea that I need to get through your head, and we may need to retrain some people's intuition. So I'm gonna say the idea. I'm gonna say it a second way, and then I'm gonna give you a few examples to try to drill the idea into your head. Okay. Only after that, only after we've worked through this idea am I going to finally work out the mathematics of this more general projectile motion. All right, here's the idea we need to discuss now. So I'll say it one way first. Gravitational acceleration is completely vertical. Okay, hence it does not affect the horizontal component of velocity. Okay? So all I'm saying here, which you already knew, the gravitational acceleration vector is straight down. There's no horizontal component. So that means that the horizontal velocity of something moving through the air, like a golf ball or a baseball, the horizontal component is gonna stay constant. Okay, that's significant. You have the vertical velocity component. It's getting fat. The speed is increasing. The absolute value velocity of the vertical component is increasing because of gravity. But horizontally, it's nice and simple. The horizontal component is constant. Okay, let me say it in a more intuitive way. In a sense, the vertical and horizontal motions of a projectile are independent of each other. Okay, the reason that's an attempt at a different way of saying the first way I said it is that you have all this drama happening in the vertical, right? The velocities, it's getting faster and faster, vertically speaking, and then the horizontal is just happily, right? It's just moving horizontal. The horizontal component doesn't change. So that's what I mean when I say that they're independent. Okay? Now let me give you several examples of the implications of this. All right. So if I had a cup and I dropped a tiny ball above the cup, if I let go of a tiny ball above the cup, I think you would agree that it would fall into the cup. No surprise there. All right. However, what about if I was holding the cup in my hand? I was sitting in the back seat of a car going 65 miles per hour on the freeway. Okay, and I held the same ball above the cup in my other hand, going 65 miles per hour down the freeway. Now, if I drop the ball again, what's going to happen? Is it going to land in the cup? Okay, the answer is yes. Okay, I think you would agree that if I let go of a ball while traveling in a car at high speed, it's not going to go flying out one of the windows. Okay, it's going to behave as if what's happening vertically is not affected by the horizontal motion. All right, that's an example of what I mean by these ideas, where the horizontal and vertical are independent. Okay. Another example I want you to think about is, suppose that I fired a gun at a certain height. And so the bullet is going to get fired out the gun, fire it horizontally, and it's going to make whatever trajectory it makes, okay? And at the same time, suppose that I drop the bullet from the same height. Which one's going to hit the ground first? Bullet number 1 that was dropped straight down, or bullet number 2 that was fired at the exact same instant horizontally from the same height? Okay, now the answer is that they will both hit the ground at the same time. You can Google on YouTube for a Mythbusters video where they actually did this, and they took high-speed video and they confirmed that both bullets hit the ground at the same time. Okay, now once again, just like dropping the ball in the cup while sitting on the back seat of a car on the freeway, notice for this example that the horizontal motion had no impact on how long it takes the bullet to hit the ground. Okay, so this is what I mean when I say that the horizontal and the vertical are independent. They're not affecting each other. Okay, so think about that, make sure you're comfortable with this idea, and we're going to use this to simplify the mathematics of projectiles. All right, so here's the questions that I want to ask. First of all, let's do the guy running off the roof. The questions I'm going to ask for projectiles are: how long does it take to hit the ground? How long is it in the air? And how far horizontally does it go? Okay, so somebody runs off and they land in the pool or whatever, and so they ran off. Let's say they had a height h, and let's say that they ran off the edge, they ran off the roof with the initial velocity v0. Okay, so the questions we want to ask are: how long was the projectile, in other words the person, in the air? How far horizontally did the projectile go? And also how, let's see, I guess that's for this one, that's it. For the golf ball, we'll want to know not only how long was it in the air and how far did it go, but we'll also want to know how high it got. Okay, so let's do how long was it in the air. Okay, now think back to what I said about the fact that the horizontal and vertical were in a sense independent. Okay, so what that means, and also think back to the bullet, the gun example I was talking about. That means that to calculate how long this projectile, this person, is going to be in the air, can't I just drop something from the same height? Right? That's going to be in the air for the same amount of time. Okay, so let's go ahead and calculate that. If I drop a penny from a height h, how long does it take? Well, let's use delta x equals v0 delta t plus 1/2 a delta t squared. So it's going to go a distance h, starts with initial vertical velocity 0. Okay, notice that even the guy running off the roof, he had a v0 that was a horizontal velocity, but notice even he had no vertical component of velocity initially. Okay, and then 1/2, if you want to make down be negative, then the delta, the change in the y coordinate, the change in position, the displacement would be a negative h. Okay, if you did that, you'd have to put a minus g here. Okay, and then the time squared. And so now you can solve, you could solve for t squared, so 2h over g equals t squared. So the time that it's in the air is the square root of 2h over g. Alright, there you have that. And now how far did the projectile go? Okay, when they talk about how far horizontally it went, people will often refer to that as the range. Okay, even golfers will say, you know, what's your range? How far can you drive the ball down the lawn, the field? Okay, so now think back to what I said, that the horizontal component of a projectile, of the velocity, just happily stays constant. Okay, so forgetting about the vertical, you can, to calculate the range, all you have to do is ask yourself, if I was in a car driving for a certain amount of time, how far would I go? Okay, and the amount of time that we're allowed to move down the move in the horizontal direction is the time of flight. Okay, how long, the answer to the first question, how long the projectile was in the air. So what I'm saying is that the range, how far it went, is the x component of velocity times how long it was moving in the horizontal direction. Okay, well, the x component, the horizontal component of the velocity, is going to equal the initial, because we said the horizontal component doesn't change, and the time that it gets to move horizontally is the time of flight, so 2h over g. Alright, so there you have it. See, do you see how I was able to simplify a relatively complicated projectile question by first I ignore the horizontal and do something in the vertical direction, then I ignore the vertical and focus on the horizontal. Okay, that idea comes up all the time with projectiles. So there you have it for somebody running off a roof horizontally. Okay, let's finish with one more example. Let's do the golf ball or baseball where it goes up and down. And let's say this time, let's say that it starts with we'll give it a certain velocity v0, and we'll also have to give it an angle this time. So we'll say this is theta and this is v0. Okay, so what is the initial x component? The initial horizontal x component, well, that would be using our vector knowledge, v0 cosine theta. The initial vertical velocity the vertical velocity component would be v0 sine theta. Alright, so once again we have the same questions we had before, plus one more. Time of flight, range, and max height. That's what we want to calculate for this situation. Alright, so let's do the time of flight. So again, we're going to ignore the horizontal for a second, and we're going to ask ourselves, if I threw something straight up with a velocity of v0 sine theta, because isn't that the initial vertical component of the velocity here? So if I throw something up with that vertical velocity, how long is it in the air? It goes up and down. Okay, well, let's see. Well, in that situation, delta y would be 0 between the beginning and the end if it goes straight up and comes straight down. The time is what we're looking for. Okay, and you know what, in order to solve and then we have the acceleration is minus g. Let me see if that's enough. Can we think of it? Can we get a kinematic equation that can solve that? Let's see. Delta y equals v naught y delta t plus 1/2 a times delta t squared. Yes, we can do this. Okay, so 0 equals v0 sine theta times mystery time plus 1/2 times minus g times mystery t squared. Alright, now I want to divide both sides by t, so I get 0 equals v0 sine theta minus 1/2 gt. So moving everything around, I get that t is equal, you can do the algebra yourself, you'll get v0 sine theta, 2 v0 sine theta times, divided by g. Okay, so there's the time of flight. Okay, look that over, make sure you understand how that worked out. Okay, again, notice I ignored the horizontal when I was calculating the time of flight. That's the game we're going to keep playing. Alright, now let's do the range. Okay, the range, the delta x, is, well, remember the velocity is constant in the horizontal, so we're going to use vx naught, and we're going to multiply by how long it was moving in the horizontal direction. So that gives v naught cosine theta, and then for the time we're going to use 2 v naught sine theta over g. So we'll call the range r. So simplifying that, we get 2 v naught squared sine theta cosine theta all over g. So that time we ignored the vertical, didn't we? Alright, so we've got time of flight and we've got range. Now we need to get the max height. Alright, now in order to solve for the max height, you need to see that at the very top the vertical component of the velocity is 0. Okay, why is that? Well, as something moves up, gravity is slowing it down, slowing it down, slowing it down, and right before it starts to come back down, it's slowed down to where it's 0, and then it's going to start, of course, in the next few seconds start becoming negative. Okay, so let me work that out here on the left side, and I'll do that in a different color. So for that situation, we start out with a velocity of v naught sine theta, and we are going to have a final velocity at the very top at the max height of 0. We have still the same acceleration as always, minus g. Okay, and so to find the max height, we will use this kinematic equation. Delta v squared equals 2a delta x, the one that doesn't have time. Okay, so v final squared v final y squared minus v initial y squared equals 2 times minus g times the max height, let's call it capital H. And the final, that's 0. Okay, so we've got, and then we could multiply both sides by minus 1 to get rid of those negatives. So what do we have? We have v naught sine theta for the left side, v naught squared sine squared theta equals 2gh. Okay, isolating h, you have to divide both sides by 2g, and that gives you the max height. Let me put that in the bottom right. The max height is v naught squared sine squared theta over 2g. Alright, so we've worked out all the mathematics for the most complicated, or one of the most complicated projectile motions. Okay, notice that the range equation has 2 sine theta cosine theta. You can, if you remember your trigonometry, you might recall that that's the same as v naught squared sine sine of 2 theta. Okay, that's useful sometimes. But let me point out that if you do that, the range equation is doubling the theta. So the angle is being multiplied by 2. Look at the height equation. The max height equation, the theta isn't multiplied by 2, but rather the sine is being squared. Alright? And then the time of flight, 2v, in that situation, the sine function is not being squared, the angle is not being multiplied by 2, but rather the whole sine function itself is being multiplied by 2.